Hello everyone and welcome to today's webinar. Before we get started, I'd like to go over a few items so you know how to participate in today's event. You have joined the presentation listening using your computer speaker system by default. If you prefer to join over the telephone, select the arrow next to the mute, unmute icon on the bottom of the Zoom screen. Select Leave Computer Audio and then select Phone Call and follow the prompt to dial in. You will have the opportunity to submit text questions to today's presenters by typing your questions into the questions pane of the control panel. You may send in your questions at any time during the presentation. We will collect these and address them during the Q&A session at the end of today's presentation. And now I'd like to introduce Glenn McGilvery from ICLR. Glenn?
Thank you, Tracy. Hello, everybody. Good afternoon. Glenn McGilvery, Managing Director of the Institute for Catastrophic Loss Reduction. Thanks for joining us. We're fortunate to have with us today Dr. Nathan Gillett and Dr. Xuebin Zhang. Nathan is a research scientist. Xuebin is a climate research scientist, both with Environment and Climate Change Canada. And they're going to give us an important rundown on the Canada's Changing Climate Report. And just before I hand it over, just let me note that, keep an eye on your inbox for future notices for the next Friday Forums. And now I'll hand it over to Dr. Gillett and Dr. Zhang.
Thank you very much. So this is Nathan Gillett here from Environment and Climate Change Canada. I'm going to be talking about the first part of the report, giving an overview of Canada's Changing Climate Report. And then I'll be handing over to Xuebin Zhang, who will deal with particularly with the extremes aspects of this report, which is going to be a particular focus of the presentation today. So Canada's Changing Climate Report was a collaborative effort between Environment and Climate Change Canada, Fisheries and Oceans Canada, Natural Resources Canada, as well as other university experts who joined the author teams of some of the chapters. Sorry, there we are. Okay, so Canada's Changing Climate Report is the first report in a series of reports which form Canada's national assessment on climate change. So as you can see in this diagram, phase 1 is the report that we're going to be talking about today. Phase 2 are a number of sector assessments which focus on impacts of climate change Canada, and then those will be followed by a third synthesizing across these different reports. So the report that we're going to be talking about today, Canada's Changing Climate Report, which came out at the beginning of April, is really laying the climate science foundation for the rest of the reports which focus on impacts of climate change in Canada. So I'll be talking you through the key conclusions of the report. So starting at the beginning, Canada's climate has warmed and will warm further in the future, driven by human influence. Global emissions of carbon dioxide from human activity will largely determine how much warming Canada and the world will experience in the future. And the warming driven by carbon dioxide is effectively irreversible. So I'll illustrate these points a bit more in the next slide. So the figure on your left is taken from the 5th assessment report of the Intergovernmental Panel on Climate Change. It shows how global average temperatures change in response to cumulative emissions of carbon dioxide. So on the x-axis, on the horizontal axis, is the cumulative emissions of carbon dioxide since 1870. So that's just the total amount of carbon dioxide emitted since 1870. And on the y-axis is the warming in the global average temperature. You can see several things on this figure. The first one is, if you look at the black line, that's carbon dioxide only, that the warming driven by carbon dioxide is closely proportional to the cumulative amount of carbon dioxide emitted. And it doesn't really matter exactly which pathway emissions scenario we follow. It's really the cumulative amount of carbon dioxide emitted which determines the global warming. The colored lines show scenarios which also include other forcings, other non-carbon dioxide greenhouse gases and aerosols. You can see that those warm a bit more than the carbon dioxide only simulation, so the net effect of those other forcings is to drive a further warming. But still the warming is is fairly scenario independent. So one consequence of this is that if we look on the y-axis, we can pick a temperature threshold such as the 1.5 degree or 2 degree temperature thresholds identified in the Paris Agreement, and we can read off a corresponding emissions budget, a corresponding amount of cumulative carbon dioxide emissions that we need to limit emissions to if we want to avoid exceeding that temperature target. So as it says in the text below, different temperature limits have different carbon budgets, different remaining cumulative carbon dioxide emissions that we must not exceed if we want to remain below that temperature target. Another consequence of this proportionality between warming and cumulative carbon dioxide emissions is that to stabilize climate, we need to reduce carbon dioxide emissions to zero. The figure on the right shows simulations of from an early version of the Canadian Earth System model. The black line shows simulations driven by historical changes in carbon dioxide, followed by a scenario of future emissions to 2100, so increasing carbon dioxide. And then the two colored lines show simulations in which carbon dioxide emissions are set to zero. So there's no further carbon dioxide emissions in these simulations. And as you can see, the global average temperature stays approximately constant. And if you look at the x-axis, these simulations were carried out to the year 3000. So on centennial to millennial timescales, global average temperature stays constant even after emissions of carbon dioxide cease. So that's what the report means when it talks about the irreversibility of carbon dioxide-induced climate change. Okay, let's move on to the next slide. So focusing more now on climate change in Canada. Canada has warmed, and it's warmed faster than the global average. So in the figure on the right, you can see in blue the average temperature over Canada in the period since 1948. You can see there's been an upward trend, and that temperature over Canada has increased by 1.7 degrees Celsius between 1948 and 2016. And this warming rate is about twice the global average warming rate, which is shown by the red line on the same figure. Within Canada, the warming has not been uniform, and the strongest warming has been observed in the north and the northwest. You can see that in the figure on the left, which shows trends, geographical trends across Canada over this period. So northern Canada has warmed by 2.3 degrees Celsius over this period since 1948, and that's about 3 times the rate of global warming. Most of the observed increase in average annual temperature in Canada can be attributed to human influence. So human influence is the dominant driver of this warming. Moving to the next slide, but it's not just in the average temperature across Canada that we can see the effects of human-induced climate change. The effects of warming are evident across many indicators, and I'll discuss some of those in this and subsequent slides. So the panel on the left shows changes in average annual precipitation, so that's rain and snow, across Canada over the period from 1948 to 2012. You'll see there's mostly green colors across the country, which reflects an increases in Canada, increases in precipitation observed over most of Canada since 1948. And averaged over the country, normalized precipitation has increased by about 20% over this period. And this increase in precipitation over Canada is in line with expectations from climate models, which show an increase in precipitation over northern mid-latitudes and the Arctic in response to human-induced climate change. The panel on the right shows changes in the length of the growing season, which, as you can see, has increased over almost all of Canada. So an increase in growing season length of about 15 days between 1948 and 2016 has been observed. And this, of course, is consistent with the overall warming that has been observed. Moving to the next slide, and this starts to deal with the topic of extremes. So more extreme heat and less extreme cold have been observed in Canada. The left panel shows the highest daily maximum temperature, so that's the trend in the hottest daily temperature, the hottest maximum temperature in the year. You can see that there's mostly warming trends. the annual highest daily maximum temperature averaged over Canada increased by 0.61 degrees between 1948 and 2016. And on the right, you can see the trends in the lowest daily minimum temperature, so that's the trends in the coldest temperature observed in the year. And the annual lowest daily minimum temperature averaged over Canada increased by 3.3 degrees over this period between 1948 and 2016. So there have been warming trends in both the maximum and the minimum temperature over the year, but there's been a larger trend observed in the lowest daily minimum temperature, and this is consistent with a stronger warming signal observed in winter than in summer, which is also consistent with climate model projections. And of course, the coldest minimum temperature can have, of course, impacts such as on survival of pest species. We might think of, for example, the mountain pine beetle. So certainly that warming of the lowest daily minimum temperature can be important for impacts as well as changes in the maximum temperature. Most of the observed increase in the coldest and warmest daily temperatures in Canada can be attributed to human influence. Moving to the next slide, this warming has also had effects on the cryosphere in Canada, so on snow, ice, and frozen ground, and that's what's shown in this slide. So the figure on the left, over land, you'll see changes in snow cover duration. So those brown colors over land reflect a shorter snow season, a shorter period with snow on the ground. The changes shown are between the 1980s and the decade from 2006 to 2015. And again, if you look over Canada, you can see mainly brown colors reflecting a shorter snow season, and that's also reflected throughout the rest of the northern high latitudes. Over oceans, the colors are showing changes in the sea ice cover duration, and again, you can see brown colors around the Arctic and Atlantic coast of Canada, reflecting a shorter sea ice season observed around Canada's coasts. The middle panel shows changes in glacier cumulative thickness. So this is for 3 ice caps in Canada's Arctic, the Devon ice cap, the Megan ice cap, and the Melville South ice cap. You can see in all 3 cases there have been decreases in cumulative thickness observed over the last 40 or so years. There have also been decreases observed in glaciers in the Rocky Mountains as well. So throughout Canada, we're seeing decreases in glacier thickness. The figure on the right shows changes in permafrost temperature. These are for 2 stations in the Mackenzie Valley. You can see there's been warming observed in both of these locations. And of course, permafrost temperatures are important because, well, if the permafrost temperature increases to above freezing, then we begin to see permafrost thaw. This can have important implications both for infrastructure, for roads and buildings that are built on permafrost, and also in terms of a climate feedback. As permafrost thaws, we expect to see release of carbon stored in that permafrost, both as carbon dioxide and as methane, and that can act as an important feedback on climate change. So over the past 3 decades, the proportion of Canadian land and marine areas covered by snow and ice has decreased, permafrost temperatures have risen, and Arctic and alpine glaciers have thinned at rates which are unprecedented for several millennia. Moving to the next slide, which is concerns future changes in the cryosphere in Canada. So Canadian areas of the Arctic and Atlantic Oceans will experience longer and more widespread sea ice-free conditions. So we've already observed a decrease in the sea ice season around Canada's coast. That trend is expected to continue into the future. Canadian Arctic marine areas are projected to have extensive ice-free periods during summer by mid-century. But if we think about the context in terms of the whole Arctic, the last area with summer sea ice is projected to be an area that's around and north of the Canadian Arctic archipelago, which is shown schematically on the map on the right. And so this area will be an important refuge for ice-dependent species, as well as an ongoing source of potentially hazardous ice drifting into Canadian waters. As the ice thins, it can become more mobile, and so it can remain a hazard for navigation. But as I summarized on the start of this slide, we can expect ongoing decreases in ice cover season in Canadian waters. So at this point, I'm going to hand over to Xuebin Zhang, who will take you through the rest of the presentation, focusing on changes in freshwater and changes in extremes.
Nathan?
Yes, Xuebin, we can't hear you. Perhaps he's still on mute.
Okay.
Okay, sorry that. Good afternoon and welcome. I'm Xuebin Zhang from Environment Canada in Downsview. The seasonal availability of fresh water has changed, and the change is projected to continue. This brings an increased risk of water supply shortages in the summer. Changes in fresh water are driven by a combination of changes in temperature and changes in precipitation, snow accumulation, melt, and in mountainous regions of Canada, melting glaciers are also a factor. Over the last few decades, warmer temperatures have caused a spring peak stream flow following snowmelt to occur earlier, with higher winter flows. In rivers with their headwaters in the mountains, reduced summer flows have been observed due to smaller high elevation snowpacks. Continued warming and associated reduction in snow cover and shrinking mountain glaciers are expected to continue to drive changes in the seasonality of stream flow, as we'll see on the next slide. The finding about warmer summers, increased evaporation of surface water, is an important part of the story about potentially drier summers in the future. Even if there are small increases in precipitation projected in summer, under low emission scenarios, this may not be sufficient to compensate for increased evaporation and evapotranspiration. This alone with projected lower summer stream flow increase the risk of water supply shortages during the summer season. Okay. Now move to the next slide. The most notable feature of observed changes in stream flow over the last 5 decades involves changes in its seasonality. We illustrate this in the schematic as shown on the slide. This figure documents the annual cycle of stream flow resulting from snowmelt. The red line shows the peak in the spring as the snow melts and decrease throughout the summer. The green line represents changes we have already seen and can expect to continue in the future. So, in the other words, that's the when you can think about the red is in the past, and the green is something that has already occurred. Spring peak stream flow following snowmelt has become earlier, along with higher winter flow. In rivers with the headwater in the mountains, summer flows have been reduced. Seasonal changes projected to continue with shifts from more snowmelt-dominated regions toward rain-dominated regions. Lisa mentioned earlier that most observed temperature increase can be attributed to human influence. Here, I will provide a little more details on this. Most of the warming we have observed can be attributed to human influence on climate, primarily through emissions of greenhouse gases. The figures here demonstrate observed temperature increase over Canada from 1948 to 2012 in navy blue, and an estimate of the temperature increase after removing the impacts of internal climate variability in gray. The similarity between the blue and the gray bars indicate that internal variability is playing only a small role in the temperature trends we've seen, especially for extremes on the bottom row. This means some sort of force external to the climate system is driving this warming. We can then compare observed trend to climate model simulations with different forces to determine what those driving external forces are. In green is a trend attributed to all external forces, which is a combination of anthropogenic effects and natural external factors. The trends attributable to these two components are shown in red for anthropogenic or human factors, and in bright blue for natural external factors, which include solar and volcanic activities. The red bar is fairly similar to the green and gray bars based on all external forces, which tells us that anthropogenic or human forcing contributes most of the increasing trend in temperature. Natural external forcing provides only small contributions, increasing warming for annual mean temperatures and for the hottest temperatures of the year, and decreasing the warming for coldest temperatures of the year. Canada is also seeing the impact of climate change on the occurrence of extreme events. Anthropogenic or human-caused climate change has increased the likelihood of some types of extreme events. Of course, extremes occur regardless if there is a change in the climate. Because of this, it is almost impossible to answer if a particular extreme event is caused by change in the climate, such as what we have seen, the Ottawa River flood. Nevertheless, we can ask a question if the probability or the magnitude of an event has been affected by change in the climate. This idea is illustrated in the schematic figure on this slide. We have assessed the several case studies that conducted for different extreme events that occurred in Canada, and here we provide two examples. Using climate models, we are able to determine how often particular events would be expected to occur if the climate was driven by only natural factors, and compare this to how often these events are expected to occur in a climate impacted by humans. We can then determine how anthropogenic climate change has changed the odds of experiencing the major extreme events, and we could also look at how much the changes in the magnitude could have been. For example, the 2013 Alberta floods occurred with an increased likelihood of extreme rainfall that produced that flood. And the 2016 Alberta wildfire occurred with increased likelihood of extreme wildfire risk and of longer fire seasons. Human influence on the climate is responsible for much of the warming already observed and the related changes in extreme events. If warming trends continue, we can expect many types of extreme events increase in frequency and or intensity. Now I'll talk a little bit about the future projections. In the future, Canada will continue to warm, but the amount of future warming will depend directly on global emissions. On the left, the time series shows the temperature change averaged for the Canadian land area and over the 1900 to 2100. The thin lines show results from individual climate models to demonstrate a range of model projections, and the heavy line is a multi-model mean. The gray and black lines are the historical simulations, followed by two different possible scenarios for the future. In blue is the low emission scenario, broadly consistent with the Paris Agreement goals. In red, a high emission scenarios, it's a representative of business as usual conditions. Canada will see some warming under the low emission scenario, with temperature leveling off around the mid-century. Under the high emission scenario, where we see continued increase in greenhouse gas emissions, Canada sees much greater warming that continues beyond the end of the century. On the right is a map of projected temperature change by the end of 21st century for winter over Canada for the high emission scenarios, using the median of the CMF5 multimodal ensemble. Warming will be strongest during winter season and over northern Canada. Winter temperature increase are large, projected in between from 5 degrees in the southern part of Canada to more than 10 degrees in northern Canada. Warming in Canada, as in many other regions, is closely related to changes in global mean temperature. In the figure on the left, we are plotting global mean temperature on the horizontal against the Canadian mean temperature on the vertical. Canada temperature is consistently about twice the global temperature. That was what we see in the observations, and this is also what we see in the model projections. And this is independent of the future emission scenarios indicated by the colors. There are two aspects on here. One is that if you recall what Nathan mentioned about the connection between the global emission or the global total carbon budget and global mean temperature change, you see a direct connection between global warming levels and total carbon in the system. And here, what we see is the linkage between the global mean temperature increase and the Canadian mean temperature increase. So, which means that the Canadian mean temperature is closely related to the global total carbon in the atmosphere. Similarly, many impact-related metrics also scale with temperature. Here we give example of the length of growing season. That is plotted on the right panel against Canadian mean temperature. This linear relationship can be used to help us understand and estimate future changes in temperature-driven indices. A warmer climate will bring more precipitation on average. Increases are projected for annual precipitation, as well as for winter, spring, and autumn everywhere in Canada over the 21st century. The figure on the left shows projected changes in winter precipitation average over the country. The low emission scenario in blue corresponds to a small increase, while the high emission scenario in red is associated with larger increase in winter precipitation. For summer, the results are not consistent across the country, especially when in the high emission scenario towards the later 21st century. In northern Canada, summer precipitation is projected to increase, similar to other seasons. However, as shown in the figure on the right, when the warming is strong, such as in the late 21st century, under the high emission scenario, a small decrease in summer precipitation is projected for southern Canada. So the projected decrease in the summer precipitation under this condition, as well as projected fairly strong increase in summer temperature, which will lead to larger evaporative power, means that there would be a water shortage problems in the summer. A warmer climate will intensify some weather and climate extremes in the future. Extreme hot temperature will become more frequent and more intense. This will result in an increase in the severity of heat waves and contribute to increase of drought and wildfire risks. The projected decrease in summer precipitation in some regions on a high emission scenario that were mentioned earlier will make these drought and wildfire risks even worse in these regions. Periodic drought have occurred across much of Canada, but no long-term changes are evident. Future soil moisture deficits are projected to become more frequent and intense in some areas, which translates to more severe drought conditions. Canada experiences several different types of flood that are caused by many factors. For example, heavy precipitation is the main cause of urban floods, and the projected increase in heavy precipitation will result in an increased future risk of urban flooding. Other types of floods, such as those driven by high stream flows or excessive snowmelt, are often affected by multiple factors, include excessive precipitation, rapid snowmelt, ice jams, rain on snow, or combination of these factors. It is difficult to project some of these factors, and it is also difficult to know how projected changes in these factors will interact with each other in the future, and as a result, potential changes in these types of flood are uncertain. For example, the recent flood in Ottawa that it's affected by the large by the melt of the large snowpack that accumulated over the entire winter. So on one hand, in a warmer climate, we would expect to see more precipitation amount in the winter, which can help with higher accumulation of precipitation. On the other hand, the warming in temperature during winter also reduce the season, reduce the length of season when the snow accumulation can occur. So then, in the future, the river flood like the one we have just experienced will have something to do with this kind of offsetting effect on one hand of increasing in precipitation, and then on the other hand, reduction in the snowpack season. So for that reason, it's very hard to know how much of climate change have affected the magnitude frequency of this kind of flood in the past. And it's also very hard to project how such a kind of flood will change in the future. A common way to measure the severity or frequency of extreme events is to calculate average wait time between similar events. This time is called a return period. For example, at 36 degrees Celsius, air temperature in Ottawa has a 20-year return period. This means that this extreme high temperature is recorded on average once every 20 years. A reduction in this return period means that a similar event, such as a 30-degree sea temperature, occurs more often. The figure to the left shows projected changes in return period of hottest daily temperature under high emission scenarios average over Canada. As shown by the green line on the figure, the hottest daily temperature that occurs once every 20 years in the late 20th century climate is projected to occur once every 2 years by the middle of the 21st century. This means that these extreme high temperatures is projected to occur 10 times as often. The figure to the right shows projected changes in the return period of greatest one-day precipitation amount that's recorded during the year. Again, under the high emission scenario, as shown by the green line on the figure, extreme precipitation value that occurs once every 20 years in the late 20th century climate is projected to occur once every 10 years by the middle of the 21st century. In other words, this amount of extreme precipitation will occur twice as often. Global sea level has risen and will continue to do so. The projected amount of global sea level rise is many tens of centimeters and may exceed 1 meter by 2100. The main contributors to global sea level rise are warming and expansion of the surface layer of the oceans and waterfront diminishing glaciers and ice sheets. Regional changes in sea level vary, however. Along Canadian coastlines, changes in vertical land motion are the most important regional factor affecting relative sea level change or local sea level change. Land uplift and subsidence are occurring in different places due to delayed rebound of the land following the last deglacialization. Relative sea level is projected to rise or fall depending on local vertical land motion. Those areas along Canadian coast where sea level is projected to rise are noted by warm colors. In the figure, sea level is projected to rise at slightly more than the global amount in some parts of Atlantic Canada. Those symbols are about anywhere between 75 to 100 centimeters of projected sea level rise. Other places where sea level is projected to rise are the remainder of Atlantic Canada, British Columbia, and above the coastal airline in the Arctic. In contrast, for Hudson Bay and much of the Canadian Arctic archipelago, the land is rising so quickly that the local sea level is projected to fall. Coastal flooding due to extreme high water level events will increase where sea level is projected to rise. For example, for 40 centimeter sea level rising at Halifax, which would be reached around the mid-century for a high emission scenario, and 1 in 50-year flood event will occur on average once every 2 years because of the rise in the local sea level. Projected reduction in sea ice in Atlantic and Arctic Canada will also contribute to increased flooding and erosion because wave actions and storm surges will increase with decreased sea ice. The rate of the magnitude of warming under high values of high versus low emission scenarios project to fairly different futures for Canada. While our report does include results for other emission scenarios, we emphasized the low and high emission scenarios to facilitate communication around choices ahead of us. The maps here illustrate this for changes in annual mean temperature towards the end of the century, and you can see the stark differences between the two scenarios. The map on the right shows warming on the high global emission scenario that assumes continued growth in global greenhouse gas emissions. Large and rapid warming during the 21st century are projected under this scenario with profound effects on Canadian climate. The map on the left shows warming on the low global emission scenario. While warming in this scenario is clearly much more limited in it is nonetheless important to recognize that additional warming and associated changes in climate will be experienced. We are already seeing the effects of widespread warming in Canada at the current level of warming. Additional effects are unavoidable. It is clear that adaptation to changing climate is imperative. Achieving a future with limited warming requires Canada and the rest of the world to reduce carbon emissions to near zero around mid-century. The science is clear then that urgent action to reduce emissions is needed if this future, which is consistent with achieving the long-term temperature goals of Paris Agreement, is to be achieved. Finally, we summarize a few main points regarding climate change and extreme events. First, the magnitude of future warming will be determined by how much greenhouse gases we keep emitting or the extent to which we are able to mitigate. Canada has already observed increases in the hottest temperatures of the year and even larger increases in the coldest temperatures of the year. For the future, larger changes are projected for temperature extremes, with more extreme hot and less extreme cold. Warmer temperatures are accompanied by an increase in atmospheric moisture, which increases extreme precipitation. The change in extreme precipitation we would expect from this relationship is too small to be consistently detectable over the observed record. However, our climate models show consistent projections that match our understanding of the physics, so we have high confidence that we will see a robust increase in extreme precipitation with further warming. Finally, extreme events can be very localized. Variability at the local scale is high, and as a result, observed changes or projections based on model simulations of particular location are highly uncertain. Information and model projections for large scales are more robust. We can use this large-scale information along with our theoretical understanding of the climate system to understand future changes in local relevant climate extremes and to guide our future adaptation effort. Thank you very much.
Thanks so much to Dr. Gillett, Dr. Zhang. We're going to move into the question and answer period right now. At this point, we only have one question that was submitted online. I have a few of my own, but we'll start with the online question. High temperatures with humidity can be fatal. One example is Russia in 2010 when 700 people a day were dying from heat. Do we have information on how much of an increase in days over 35 degrees Celsius we can expect in major Canadian population centers?
Perhaps I can answer this. We don't have this particular information as yet, but we do have ongoing work that's looking into what we call a global wetboard temperature that's more relevant for the health impact. So we are looking at our regional model simulations and also the global model simulations, and to try to estimate this kind of a heat wave with the consideration of changes in the humidity. It is ongoing, but we expect to have something published within a year, something like that.
Okay, thank you. Just a few questions of my own until we may see some others online, but I think it's generally understood that northern latitude countries will feel the impact of climate change more than equatorial countries. And indeed, you know, the Canadian Arctic is warming at about 3 times the international rate, Canada itself about 2 times the international rate. Why is this? Why is this the case?
Nathan here. Yes, I can speak to that. So there are a number of feedbacks that contribute to this stronger warming in the high latitudes, this which is sometimes called Arctic amplification. One well-known feedback is that snow and ice are bright, they're white, they reflect a lot of sunlight, and that tends to keep the surface cooler than it otherwise would be. So when we melt snow and ice, more sunlight is absorbed by the darker surface of the ground and of the ocean, and that contributes to additional warming in high latitude regions. But there are other feedbacks. One is, for anyone with a physics background, the amount of infrared radiation that the ground emits scales with to the 4th power of temperature, and this basically means that you have to increase the infrared emitted by the surface by a certain amount. In a cold region, you have to have a stronger warming than you would in a warmer region. So that's another feedback that contributes. So there are a number of different feedbacks, but those are 2 of the most important ones that contribute to this stronger warming in the Arctic.
So you bring up an interesting topic, and I actually have it here farther down my list, but I find the idea of the feedback loops really fascinating. Can you explain them in more detail and maybe give a few other examples of feedback loops that people will understand?
Sure, yes. I mean, so the concept of a feedback is some change in the climate system, which, in the case that we're thinking, which is driven by climate warming and which amplifies the climate warming that initiated it. And so that reduction in snow and ice, that ice albedo feedback as it's called, is one of those processes which contributes to amplifying. It's a positive feedback which amplifies the warming more than we would otherwise have. Another feedback which relates to something that Xuebin already talked about is the water vapor feedback. The amount of water vapor in the atmosphere is controlled mainly by the temperature of the atmosphere. A warmer atmosphere can hold more water vapor. And so as we see climate warming, the atmosphere can hold more water vapor, we get more evaporation. But at the same time, water vapor is a greenhouse gas. So if we have more water vapor in the atmosphere, that will act to amplify the warming. So that's another positive feedback. There are a number of both positive and negative feedbacks in the climate system, which are important to quantify and understand if we're able to predict future climate change. One more, which I've already touched on, which I can speak to a little bit more, is the permafrost feedback, about which there's quite a lot of uncertainty. But permafrost has a lot of frozen organic matter, and that as it warms, it can start to decompose, it can release carbon dioxide and also methane. carbon dioxide and methane, of course, are greenhouse gases, so there is a potential there to amplify the warming. So that's another example of a positive feedback.
So in a sense, they can be described as kind of like vicious cycles, or vicious circles, rather.
Yes,
in a non-scientific way.
Right, they amplify the warming more than you would otherwise get. I mean, of course, it should be said there are other negative feedbacks in the climate system, which will act in the other direction. But yeah, quantifying these feedbacks is important if we're able to, if we want to constrain our projections of future warming.
So is the same thing essentially happening in the southern pole?
That's a good question. So there is some projected amplification. So, okay, if we're thinking about what's been observed to date, there has been some warming observed over the Antarctic, but the Antarctic is a very different geographically than the Arctic. So, of course, in the Arctic we have the Arctic Ocean surrounded by a lot of land. So there's a lot of land in the high latitudes of the Northern Hemisphere. In the Southern Hemisphere, we have Antarctica at the pole surrounded by the Southern Ocean, which is, well, which has the capacity to absorb a lot of heat. And so that Southern Ocean tends to warm up more slowly than the continents, and that tends to delay the warming in the Southern Hemisphere. If we look at climate model projections for future warming, we do also see some polar amplification in the Antarctic. So particularly over Antarctica, there is more warming than the global average, but the effect is less strong than in the Arctic. Another factor is that, you know, we've got ice sheets in Antarctica which are not projected to you know, melt on centennial timescales in response to climate change. So whereas in the Arctic, there's sea ice and snow, which a lot of which is projected to melt in response to climate change. So the polar amplification is larger in the Arctic. There is some projected amplification in the Antarctic, but it's bigger in the Arctic.
Thank you. Let me remind everybody that if they would like to ask a question, so please use the Q&A box at the bottom of your screen. I think when you speak to cities, insurers, and others, the sense is that extreme rainfall is getting worse in Canada. However, Canada's Changing Climate Report notes that there is no firm trend in extreme rainfall, and it notes that one of the problems we have is a fairly poor rain gauge density, a poor density of rain gauges in Canada. So we don't have enough rain gauges to be able to pick up enough data and to indicate a trend. How do we get past this? I mean, we can't fix past data. Are there other ways of determining whether extreme rainfall is indeed changing? Is there any work being done on that right now, and where are we?
I can try to answer this question. So there are a few things that we need to understand. First of all, yes, we have a very poor monitoring system for a long-term monitoring system for monitoring network for precipitation. We just don't have nearly enough network to tell us lots of great details about changes in precipitation, total precipitation, or even in extreme precipitation. And nevertheless, we are able to have a quite clear idea in the confidence that precipitation has increased over the past. However, when it comes to extreme precipitation, it becomes much harder to know if there has been an increase or decrease in extreme precipitation. And this is because the extreme precipitation has a pretty high variability in comparison with its mean. On the other hand, we do have some ideas of what might have happened with regard to extreme precipitation. The fairly simple physics tells us that when air has warmed up, when there is a warming temperature, the air can hold more precipitation, it can hold more moisture. This more moisture translated to a heavier extreme precipitation. And this is something that can be supported by theory. It is something that is shown by different kind of resolutions of climatology, including models that that simulate weather at a very high resolution, what people call convection permitting simulations. And the increase in the moisture in the atmosphere over North America and over Canada is quite clear. So we do have in observations the increase in the moisture, which should translate into increase in precipitation. However, such kind of increase should be sufficiently small for us to be able to robustly detect it. Think about when temperature increase, with temperature increase, the moisture increase about something like 7% per 1 degree temperature increase. And I think that if that all translates into increase in precipitation, and then if we factor that in, and if we think about how much temperature we have increased over the past 100 years, we would not expect to see more than perhaps 10% increase in short duration precipitation. That's some kind of ballpark sense that we can somehow derive from physical understanding. So if you think about how much is 10% increase in precipitation, that with regard to the time series that we have, the 10% increase in precipitation is actually really small compared with the natural variation of precipitation from year to year, which makes it very hard to detect it. So yes, we haven't seen evidence of increase in precipitation. And even if we had a very, very intense monitoring network, just the magnitude of increase that we expect to see will be still small for us to see such kind of increase in precipitation in a very robust way. So the network is a problem, but it's not the main problem. The main problem is that the signal to noise ratio is very low at this point. Of course, we have other means to, when we look at a smaller scale, it's very hard for us to see it because of the high noise level. And then we can look at a much wider picture, much bigger picture. So we can look at what happens in Canada. We can look at what happens in the United States. We can also look at what happens elsewhere in the entire world. And then we get a pretty good idea that anthropogenic influence has intensified extreme precipitation. That's a quite important conclusion we were able to make in the past in past research. That's the kind of thing we understand, that the human influence has intensified extreme precipitation. And then when it comes to the future projection, and we actually can see much longer time period because model simulation give us a much larger sample size. From that, we are able to conclude conclude increase in future extreme precipitation in the future, and we actually have pretty high comments about that projection. However, I want to mention that when it comes to the localized scales, it will be very hard to know based on a single point values from a model simulation to derive what change it might be, because at that kind of scale, it's still very hard to determine with a very robust constraints for the future. So in general, when it comes to changes in extreme precipitation, we need to look at not just what happens in Toronto, but we need to look at a much bigger picture.
So we have these things called engineering data sets, and they're, I believe, based on the rain gauge data. And stormwater engineers and others use them to design storm sewer systems, culverts, roads, things of that nature. Is the data in the engineering data sets problematic since the gauge network is not dense enough? Are we building future infrastructure with data that is incomplete?
If you think about, well, this is yes or no. And if you think about very localized location, yes, we don't have enough data to do that. But on the other hand, if we look at a bigger picture, look at the larger regions, we have some general ideas. So the point here is that because we don't have enough information, and then for any local regions, or any kind of a localized locations, then we cannot build something precisely to their local climate, which means that we are paying probably more cost to overcome this kind of uncertainty in our estimation.
So therefore, it would be wrong for somebody to say, look at an engineering data set and say there is no proof that that rainfall is changing, and therefore I shouldn't need to build climate change into my systems. Is that correct to say that would be a dangerous road to take?
Absolutely. You cannot say because I don't have trend in this station, there's no climate change for my place, I don't need to worry about it. That's wrong. On the other hand, if you see a huge trend in your location, you see, okay, I got a lot of changes in my place. I will need to extrapolate this trend for the future, and it probably is also incorrect because that particular the observation for that location, even if it's perfect, may not be able to represent the changes in the climate simply because the natural variability is big and then the signal of the climate change is small. So it really comes down to the bigger picture that what physics, what overall understanding of climate can tell us and can guide us. This is a kind of area that we are working on very closely with the National Research Council and also to some extent with the with SSC, with Canadian Standard Council on this to hope that we can provide good guidance for the engineers to follow.
Great, thank you. We have two great questions online. First of all, if higher temperatures mean more water vapor, can we extrapolate from that we might expect to have more cloudy days than sunny days in the future?
Nathan here, that's a good question. I'll take this one. Well, the higher temperatures mean that the water vapor can, that the atmosphere can hold more water vapor. In other words, it can hold more water in its gaseous form. How exactly clouds will change with climate is a big source of uncertainty in climate projections, both in terms of changes in low clouds and changes in high clouds. And those are an important climate. So I was talking already about climate feedback. Potential changes in clouds are an important climate feedback. However, there is large uncertainty in terms of those changes as a climate feedback. Yes, and in terms of changes in cloudy days versus clear days in Canada, there's large so it's not covered in the report, but there is large uncertainty undoubtedly in projected changes in cloudiness. So yeah, I don't think we can say anything robust about how sunny versus cloudy days will change in the future. But it's not a direct consequence of increased water vapor that we expect more cloudy days. The increased temperatures just mean the atmosphere can hold more water vapor.
Okay. Second question is, it was mentioned that we are currently past the point in reversing climate change. Would projects such as changing the albedo of cities, highways, et cetera, be able to change this effect or just slow the warming?
Okay, so first I guess to discuss what I meant by irreversible. So when I was talking about irreversible climate change due to carbon dioxide, I was thinking, what I meant was that even if we stop emissions, the global average temperature will remain approximately constant. Now, yes, theoretically, it would be possible to cool the climate in various ways. One way would be by humans removing carbon dioxide from the atmosphere, and there have been a number of ways proposed to do that, either by growing forests or growing forests, burning them and storing the carbon. There's a number of schemes that have been proposed to remove carbon dioxide from the atmosphere, and if we were able to remove carbon dioxide from the atmosphere, then yes, that would cause a cooling of the global average temperature. The question is also asking about specifically asking about changing the albedo of roofs in cities and so on. This is an approach that has been proposed to cool the climate. it would cause some cooling, but it can only, because the fraction of the the Earth's surface that is covered by buildings and highways and so on is fairly small. It only has the capacity to cause a fairly small cooling. I mean, there are other approaches that have been proposed, putting aerosols in the stratosphere, which could conceivably cause more cooling. So to get back to the question, yes, if we are able to either remove carbon dioxide from the atmosphere or increase the reflectivity somehow, then we could cool the climate.
Great. You talked about attribution studies, and I'm aware of 3 in Canada. One was done for the 2017 BC wildfire season. And then here we mentioned the 2013 Southern Alberta flooding and Fort McMurray wildfire. Are you aware of any other attribution studies being done in Canada right now, or are there other good targets that we can do attribution studies for?
Nathan here, I can speak to that. So those are, yes, those are event attribution studies, and those, I'll let Xuebin jump in afterwards. Those are, I think, they're the only 3 that I'm aware of as well. So those are studies which look at changes in the probability of particular extreme events. But there are other studies that are looking at long-term changes in climate in Canada. There have been attribution studies on average temperatures in Canada, which have demonstrated that humans are likely the dominant cause of the warming in Canada. There have been attribution studies on changes in extremes in Canada, so trends in annual maximum temperatures that we mentioned in the presentation. There have certainly been attribution studies on changes in stream flow in British Columbia. So there have been a number of attribution studies looking at trends in climate variables and finding human contributions to those trends across a range of variables in Canada.
I understand that oh, sorry.
Okay. So there's another study that's conducted by folks at Yukon, but now they moved to McGill. So that study looked at human influence to the 2013 Quebec flood. The Quebec flood was mostly a rain on snow event. So they look at it, and they look at it. So essentially, increase in winter precipitation that should result in a large accumulation of snow. But on the other hand, there was a shortening in the winter season due to the warming. So they realized there was an offsetting factor by these 2 factors, and were not able to really say much about human influence on that sort of kind of flood event in that region. So that's an additional one that I'm aware of. And we also have some ongoing work that try to attribute observed changes in precipitation over entire North America, and we were able to see quite robustly that the human influence may have increased if precipitation over North American continent.
I understand that it's difficult to do attribution studies for really localized extreme rainfall events, maybe like 2014 Burlington storm or some of the Toronto storms. Is that correct?
It is correct. And first of all, it's impossible to say if this particular storm is caused by human influence. I don't think we can say anything like that, because such kind of storm can actually occur regardless if there is a change in climate. But on the other hand, it is possible to look at how much human influence may have increased the magnitude or the frequency of this kind of storms. And this is something that has been done for example, like this Alberta flood. So I imagine it is possible to set up such a kind of studies if there's a good model to do that kind of simulation. It is possible to do.
Thank you. Well, I think that was my last question, and there are no others online. Unless anybody else has a question, I think we can probably wrap it up there. I want to thank both of you for your time. I know you're both busy. This was excellent. Very well done. We greatly appreciate it. Thanks so much.
Thank you. Yeah, it was good to participate.